Hello YouTube. In this video we're going to define radian measurement, and after watching this you should be able to both kind of understand what that is, but also sketch angles in radian measurement, or even estimate the size of an angle using radians as opposed to degrees. Okay, so let's go ahead and get started. I'll have you take a look at this image over here. You'll notice that we have a central angle, or that as an angle where its vertex is located at the origin here, and we notice that this angle is in standard position. That is, its initial side is on the positive x-axis here, and so I happen to construct this angle here, or at least do a screenshot of this angle here, and we notice that it terminates in the first quadrant. But instead of measuring this in degrees, how else might we be able to measure this? A few basic assumptions we want to start with. Given this angle right here, typically we don't draw a circle around it, but we're going to go ahead and assume that there is a circle of radius r that passes centered upon the origin here and is somewhere out here in the plane, has some radius r. So let's go ahead and label a few things here. We say r represents the radius of this circle. And the interesting thing is I don't need to label this r up here either. We know that one thing is true, the radius is the same no matter where you go on this circle. And then also this, we say s. Now in this instance here we're going to say s is arc length, and what we say is that is the length of the arc that is intercepted by our angle. So let's go ahead and acknowledge one thing. When you have an angle in standard position, and we say that we have a circle that kind of is centered upon the origin and goes around here with some radius r, our angle is going to cut off or intercept some arc on the outside of the circle, and we're going to call s that arc length there. Okay. But when we talk about radian measurement, the interesting thing is this: we're not going to, estimate this in degrees. What we want to know really is this: how big is this angle? And a convenient way of figuring this out, or at least defining this, is to say, well, the bigger and bigger this angle gets, will the radius get bigger and bigger? And we already acknowledged that no matter how big your angle gets, the radius is always going to stay the same. But maybe we could also acknowledge this: the bigger and bigger this angle gets, the longer and longer the arc gets around the outside. So essentially what we could do is we could define, first of all, what 1 radian is. We say 1 radian, by definition, is the measure of a central angle theta that intercepts an arc length s equal in length to the radius r of the circle. So what you're seeing up here is an instance where I'm saying that the arc length is actually the same exact length of this radius. So this length from here to here is the same as the length from here to here around the outside, and we're calling this 1 radian. So 1 radian would be the amount of rotation that you would have to rotate through here in this plane so that the intercepted arc is the same length as the radius here. But in general, what we can say is this: the measure of an angle in radians is always equal to however many times the radius passes into this outside arc. So that's to say that if our angle were, say, twice as big, maybe I have this angle here that's 2 times the size of our original theta here, what that would mean is then this radius would not only fit into the outside once, but it would fit into the outside twice, and therefore we would define this to be an angle that is 2 radians in measurement. So by definition, the measurement of an angle in radians is equal to, we say equal to the number of times our radius passes into the intercepted arc. Okay, and I have a formula here, and we're going to kind of commit this one to memory, but we basically say an angle in radians, we say, if you can't see that very well, we say theta is equal to the arc length divided by the radius. And the more times the radius fits into the arc length, we're just basically saying this angle is getting bigger and bigger. The interesting thing about this is that with all circles, of course, the radius doesn't change, but it is very, very much the case, and you see my diagram down here. We can see that no matter what the angle theta, if you were to rotate 1 time around, the radius always passes into that 1 full rotation the same amount of times, no matter what size circle you have, and that's always the case. And actually, I've got another diagram that I can pull up here. This is a little applet that I got off GeoGebra. Basically, taking a look at this, we say we have some central angle theta, and you'll notice that my angle theta is listed in degrees here, and I'm giving the arc length around the outside. Apparently, the arc length here is about 2.33 units, and we notice that the radius is of length 4. Okay, so considering that the radius is of length 4 here exactly, we say in general it would just be r. Basically, I want to know how many times does this radius fit into this arc, because what that does is it gives me the radian measurement. So what you'll see right here in this little box is this: you'll see that I'm taking the arc length, which is, remember, that's our S, or our arc length here, and I'm dividing it by 4, which in this case is the length of our radius. I'm really asking how many times does the radius pass into this arc length, and in this case we say 2.33. 4 goes into 2.33 about a half of a time. What I'm going to do is I'm going to kind of explore this, and I'm going to say, well, what if I were to make the arc length exactly 4, the same size the radius, okay? So I'm going to try to nail this here, and we say, well, if the arc length is 4 and the radius is 4, then the radius would fit into the arc length once, then we would say that this angle here that you'll see here is in degrees, 57.28 degrees, that's equal to itself 1 radian. So again, by definition, we say 1 radian is the amount of rotation you have to go so that the radius would fit into the arc length once. And you can see that on my image here. We say the radius would fit into this arc length once. What if we were to double the radius length here? We would see that not only would we have twice as big of the angle, but we would also say that the radius fits into the arc length twice. So we would say that this radius right here, that angle right there, pardon me, that would be a 2 radian measurement, basically saying that the radius fits in the outside twice. So if we were to double this arc and make the arc 8 units in length, 8, here you go, 8, you would say that this angle in the middle here, which is twice the size of what it started with, about 57 degrees, doubled is about 114.57-ish degrees. But we'd say that by definition, this angle in radians is equal to the arc length divided by the radius. So in this case, we would say that this is 2 radians. So the further we go around the outside, we'd say, what if my arc length was 12? Then the radius would fit into this arc length 1, 2, 3 times, and so this angle would be 3 radians right here. So as a matter of general knowing what these things are, we could say a few things about this. We would say that 1 full time around the circle would be equal to the number of times the radius fits into the arc length of 1 full time around the circle. And that's basically what I want to acknowledge first. So I want to say, if I had an angle that is 360 degrees, let me get rid of that there, 360 degrees, how many radians would this be? Well, it'd be the number of times the radius fits into the arc length. And assuming that we spin 1 full time around the circle, the interesting thing about that is, then the arc length of 1 full time around the circle would be equal to the actual circumference of that circle. So we already have a formula in general for the circumference of the circle, and that's 2 pi r. And we say that how many times does the radius go into 1 full spin, or 2 pi r? It actually passes into this, r is canceling out, 2 pi times. So we're going to set up some benchmarks here, but essentially what we can say is 1 full spin would be 2 pi radians exactly. And so you'll notice here that 6 radians is just a little bit shy of this. That makes perfect sense because 2 pi is approximately 6.28. So if 2 pi is the number of times the radius fits into the outside, then 6.28 is the number of radius lengths that fits into the outside approximately. And again over here we say, well, if 2 pi, let's go ahead and write this down, we say 2 pi radians is the same as 360 degrees, then we would say half of that would be pi radians. So we would say pi radians corresponds to this angle right here. That's approximately 3.14 of this radius length. And we can see that here. We can say 1 radius length, 2 radius lengths, 3 radius lengths, and then about 0.14 would get us all over to here. So pi is 180 degrees. In terms of other angles that we tend to situate ourselves with here, you can see that I already have my 2 pi here and my pi diagram here. Half of pi would be pi halves. So we would say half of pi would be pi halves here. That's the same thing as 90 degrees. And then 3 other angles that we tend to want to commit to memory at quite a bit of the time. I'm getting ahead of myself there. Let's put a 45 on here. And then we'll put a 30-degree angle on here. But we would say, okay, really what we're doing is we're saying that if pi is the same thing, pi radians is the same thing as 180 degrees, what fraction of pi is this? Or what fraction of 180 are these angles right here? So 60 degrees, and we can see this up here, 60 degrees is a third of pi radians right here because it consists of a third of the whole rotation there. So we could also say that 60 degrees is also a third of 180. So we would say that 60 degrees is the same thing as pi thirds radians, just like 30 degrees. 30 degrees is a sixth of 180, so this would be a sixth of pi. We say this is a pi sixth radian measurement. And then we say 45 degrees. 45 is 1/4 of 180 degrees, so it is 1/4 of a pi radian rotation. So these right here are worth committing to memory, but in general, basically what we're saying is in each of these instances up here, pi is right here, pi, pi, pi. We say we got a pi here, we got a pi here, and I've got a pi here, and of course we got a 2 pi over here. But essentially when we were talking about pi sixths, we could say that pi is the same thing as 6 pi sixths. So it would really take 1, 2, 3, 4, 5, 6 of these pi 6 things to rotate over to pi. So when we're graphing angles in radian measurement, often what we're doing is, first of all, we're just noticing what fraction of pi are we dealing with, and then we're mentally splitting up this rotation from 0 to pi up into that many pieces. So you'll notice that here when I talk about pi 6, from 0 to pi, it's split up into 6 equal sized pieces. When we talk about pi fourths, which is really a 45-degree measurement, when you talk about degrees, we would say that 4 of those fits in this one full pi rotation. And then we say that pi thirds, which is really 60 degrees, fits into a pi rotation 3 times. So for instance, this pi right here, we could be listing that as 3 pi thirds, which is the same thing as pi in the first place. Okay. So a few things really quickly, at least in terms of an angle here, we'd say that a pi rotation is about 3.14 radians. We say that 2 pi rotation is about 6.28. Half of 3.14 is about 1.57. And then if we were to get out our calculator here and we say, all right, well, 6.28 times 0.75, that'd be 75% of the way around to 6.28. We would say that there are 4.71 radius lengths when you get down to here. And we can easily see this on this picture. It would take 1, 2, 3, 4, about 4.71 radius lengths just to get down to here, okay? So what I want to do now is actually I want to kind of explore this here. I've got 3 sets of exercises to kind of look at here, but this first one here, I just want to estimate the angle to the nearest half radian, okay? So when I look at this angle right here, I say, well, how many radians is this right here? Recall that we already are aware that there are pi radians, or about 3.14 over here on the left, and there are 2 pi radians right here for 360, or about 6.28. And we already said this is about 1.57, and this is about I think it was 71 radians. But we could basically look at letter A here and say, well, I already noticed that it's a little bit past, you know, pi halves here, or a 90-degree angle. So we would say that to the nearest half radian, about how big is this angle here? I would say that, you know, given a radius length here, it would fit into the outside of this twice. Okay, not a very good image there, sorry about that. But we would say that if 90 degrees is about 1.57 radians, then something that ends about right here would be about 2 radians. So we could say that this is 2 radians. It's okay to write 2 radians. It's okay to write 2 rad. Or it's okay to just write theta. And we say radians is a unitless measure. We say just 2, okay? So letter B is a little bit different from letter A in that we've already kind of spun past pi here, so at least it's 3.14 radians. It's getting really close to a 2 pi radian measurement, or really close to 6.28. So if this is really just shy of 6.28, then I might make a guess that this is about 6 radian lengths here, because about 6 radius lengths would fit into the arc length of a circle of radius r here. Okay, and then this last one, letter C here, you'll notice that we rotated clockwise. So the first thing I want to mention here is that our angle is negative. Okay, also this, I want you to notice that it is just shy of reaching negative pi for an angle here. So if it's just shy of negative pi, or negative 3.14, we could say that this is essentially, or at least approximately, maybe a negative 3 radian measurement, and only because we rotated in a clockwise direction. So just be able to estimate the size of an angle measure here in radians. But also this, what I want to be able to do is sketch angles in standard position when they're given to me in radians. So this is something right off the bat that I say, you know, a lot of people tend to struggle with. But one thing I want to kind of draw a connection to is this. When you say 7 pi fifths, what you're really saying is we have 7 of these pi fifths radian measurements. So keeping in mind that I want to sketch this, you know, in fractions of pi, the first thing we always acknowledge is that, well, pi would be right here and 2 pi would be right here. So when I say 7 pi fifths, where would this be? What we're really saying is, well, pi fifths are kind of the fractions we're using here. So if I were to take this upper portion here and split it up into, you know, fifths, you know, this isn't a very good, you know, image here. But we would say from here over to here, right there, this would be the same thing as, and I'm going to write this in parentheses here, 5 pi fifths, because that is the same thing as pi. And over here under 2 pi, we could say, well, that'd be double of 5 pi fifths. This would be 10 of those pi fifths to get all the way around one time. But we say, well, 5 pi fifths gets me over here. I'm 2 pi fifths more than 5 pi fifths. I need to get to 7 pi fifths. So we will split this up down here, this interval from 0 to pi down here, up into fifths also. We would say that it takes 1, 2, 3, 4, 5 5 pi fifths, 6, 7, and then this would be our angle right here. So we would say that that angle measurement right there would be our 7 pi fifths radian measurement. Now, letter B, notice we have a negative angle. So we're going to be rotating clockwise here, and we're talking about pi eighths, which is kind of an irregular angle. But we say, well, what if I were to take this? This would be negative pi in this case, and this would be negative 2 pi if we're rotating clockwise. But I know this, negative 11 pi eighths, it's at least this. It's at least negative 8 pi eighths, which is the same thing as negative pi. But what we're really doing is we're saying I'm splitting this up into eighths, this interval from 0 to pi. So there are 8 pi eighths right there. We say 8 pi eighths just to get to here, and then I would need 1, 2, 3, 4, 5, 6, 7, 8. I would need 3 more pi eighths to get to negative 11 pi eighths. So 1, 2, 3, and it would stop right there. So negative 11 pi eighths would rotate from here all the way over to here, and we just rotated through 11 of these eighths of pi essentially. And then pi halves, this is kind of a big one, but we say if this is positive, first of all, we're rotating clockwise. We say here's pi, here's 2 pi. If we're talking about pi halves, one thing to do is imagine this is the same thing as 2 pi halves. And over here we could say this is the same thing as 4 pi halves. It helps to navigate sometimes when we come up with the common denominator between these originals and what we're dealing with here, which are pi halves. But we say, well, how big is a pi half? Well, it's half of a pi. So we'll take this full pi rotation right here, we'll split it up into half. So we'll just cut it in half here. We'd say it'd be 1, 2, there's 2 pi halves. I need 5 pi halves. So we're actually going to need to keep going here. I'll split this up into pi halves increments here, but we say it'd be 1, 2, 3, 4, 5 of these pi halves things. We could just label it that way, so we say 5 pi halves. So again, really quickly here, I want to, on these last two, just determine what quadrant each of these angles terminates in. And if these were in degrees, it wouldn't be a horrible thing to do, but often in radians, people kind of have a hard time with this. So let's go ahead and, why don't we just go ahead and sketch ourselves an image? So when we say 11 pi eighths, we'll be rotating counterclockwise, but the first thing I want to recognize is this. If this is pi over here, and this is 2 pi, then we would say if I'm dealing with pi eighths, it's convenient to call this 8 pi eighths. I know it would take 8 pi eighths to get over to pi, and I know it would take 16 of these pi eighths to get all the way around to 2 pi. So 11 pi eighths, if you can imagine this here, if we split this up into eighths on top, here are my 8 pi eighths, and then I would say split this up into eighths down here. It would be 11 pi eighths would be 8 pi eighths plus another 1, 2, 3 pi eighths. So our angle would be this angle right here. We would say here's 11 pi eighths, and I notice that this terminates not in the first or the second or the fourth, but the third quadrant. So we would say that this angle right here terminates in the third quadrant. And likewise with this one over here, we can kind of visualize this. We would say negative 7 pi fourths. We'll rotate clockwise. I know that a pi fourth, that's if I split this rotation from 0 to pi into 4 pieces, that would be 4 pi fourths. We'll split this top part up into fourths as well. But we'd say negative 7 pi fourths would be 1, 2, 3, 4 of these pi fourths, 5, 6, 7. So this would be right here, negative 7 pi fourths. And we notice that this terminates in quadrant 1. Okay, so that's what we mean by radian measurement, and that's how we measure angles using radians. Cheers.